Hi, my name is Guan, a former postdoctoral scholar working with Professor Henry Burton in the Department of Civil and Environmental Engineering at UCLA. I'm going to introduce our recent study on the bias-variance trade-off and its implications for machine learning applications in structural engineering. A comprehensive literature review reveals that three typical error patterns exist in the machine learning application: classical bell-shaped error, monotonically decreasing error, and double descent error patterns. In the classical bell-shaped error pattern, as the model complexity increases, the training error consistently decreases, whereas the testing error decreases first and then rises. The optimal model complexity corresponds to the bottom of the testing error curve. As for the monotonically decreasing error pattern, when the model becomes more complex, both the training and testing errors monotonically decrease. In this error pattern, no remarkable peak or minimum point can be directly used to determine the desired model complexity. The third error pattern is typically observed in some deep learning models, such as deep convolutional neural networks. As the model complexity increases, the training error decreases, reaching zero at the interpolation threshold and remaining constant. The testing error exhibits a bell shape first and then gradually decreases. To better balance the model's complexity and generalizability, this study provides a mathematical formulation. To start with, a ratio RT is introduced to determine whether the model's predictive performance on the testing dataset is comparable to its counterpart on the training dataset. A value of 1.0 for RT indicates that the model has equal performance on the training and testing datasets. A large value of RT suggests that the model's generalizability is insufficient. Similarly, another ratio named RC is defined to determine whether the testing error converges. A value of 1.0 indicates that any further increases in the model complexity would not reduce the testing error. Then an objective function is defined as a weighted average between these two ratios. The optimal model complexity can be determined by minimizing the objective function subjected to the condition that lambda should be between 0 and 0.5. To demonstrate the application of the proposed model complexity determination approach, 4 classical structural engineering problems are selected. 2 of them are classification problems, and the other 2 are regression ones. The adopted machine learning algorithms covered in these cases include decision tree, random forest, XGBoost, support vector machine, and so forth. These 4 plots show the variation of the objective function with different hyperparameters across all 4 plots. Minimizing the objective function is able to clearly indicate the optimum model complexity. Additionally, the sensitivity analysis under different lambda values demonstrate that the proposed approach is robust with respect to the lambda when it's between 0.3 and 0.5. Thank you for your listening. Please check out our paper and group website for more details of our research work.